Jai Hind. In this particular lecture, we'll talk about a sorting method, the heap sort. In heap sort method, we use sorting of a list of number with help of a heap. Heap is a tree, a binary tree, which is complete. So, in this particular lecture, we are going to cover the overview. What is heap, what is max heap, what is min heap, what are the different procedures that we use when we do heap sorting, and in this particular lecture we'll mainly discuss happify. We will do heap sort using happify method for a better efficiency and the algorithm for heap sort. So let us start with the topic of heap sort. So first point is it uses heap as the data structure. It is in place sorting algorithm. The time complexity of heap sort is order of n log n. It is memory efficient because it is using in place sorting algorithm. The same, it will do the sorting within the array. So first point is, what is heap? A heap is a priority queue and can be represented using a binary tree. Now, what are the properties of a heap? It is a binary tree with these properties. First one is structure property. What is the structure? A heap is an almost completely filled binary tree with the exception of the bottom row, which is filled from left to right. So, what it is a complete binary tree. The tree will be complete binary tree, means maximum levels will be filled, maximum filled except the last one, and in the last one all the entries will be from left to right. Second is heap order property. What is heap order property? For every node x in the heap, the parent of x is either greater than or less than equal to the value of x. If we are taking the option of greater, it will be a max heap, and if we are taking the smaller value, then it will be min heap. It depends on if we are maintaining the maximum value at top or minimum value at top. So that is our heap order property. So if I talk about this particular binary tree, it is a heap. Why? Because the parent node is greater than the two child nodes and it is a complete binary tree. If I talk about this one, it is also a complete binary tree. The last level is not having all the elements, and which elements are there? Only the last level is not having the maximum possible numbers, and the numbers which are present here, that are in left positions. If we consider this one, it is not a heap because here parent node is having value less than the child node. So these are the things that we need to consider. So this is heap, which is complete binary tree, and the value at parent node is less than equal to is greater than equal to the child node in case of max heap, and less than equal to in the case of min heap. So in this particular slides, in this particular lecture, I will talk about max heaps. We will take one example of min heap also, but the algorithm we'll discuss will be according to max heap. So I just discussed there are two types of heaps, max heap and min heap. If parent child is greater than equal to child data, parent data is greater than equal to child data, it is max heap. Otherwise it is, if less than equal to, then it is min heap. Now the example again, if I see this here, so what is the main thing we need to note down? It is in place sorting algorithm. In place sorting algorithm means we are having the sorting, we are having the given array which is to be sorted. So we can take that as a complete binary tree. How do we take it? We take a value, let me call it ith value, then its child node will be at 2ith location, and left child node and right child node will be at 2i plus 1. So what does it mean? If I am having these elements 16, 14, 10. So 16 is at one location, one index. Its left child node is twice of 1, that is 2. It is at second location. And twice of I plus 1 means right will be at third location. Same way, if I take this particular location, then the index 4 element will have child node as 2 into 4, that is 8th location, and left child node and right child node will be at 2 into 4 plus 1, 9th location. So the same array we are considering in form of a binary tree. Now see this binary tree, in this 16 is having value greater than 14 as well as 10. So it is satisfying the property of MAX-HEAP. Same way these two. Same way 8 is greater than 2 and 4. 7 is greater than 1. So this is one example of MAX-HEAP. Same way we can take mean heap. We can see here 3 is less than 7 and 5. 7 is less than 10 and 11. So these are examples of MAX-HEAP and mean heap. Now the main topic we are having is the heap sort. So how do we do heap sorting? How do we sort? How do we do in place sorting? We will consider the array. The array will be considered as the binary tree. We will represent that as complete binary tree. So first step will be build MAX-HEAP. Firstly, we will create the MAX-HEAP and then we will do the sorting after making the MAX-HEAP. Okay, so our first part is MAX-HEAP. Now let us understand the concept that when we create a MAX-HEAP, how do we do it? So let me take one small example. I am having the number 10, 5, 22, 2. So how can I create a MAX-HEAP? So what is the first value to be inserted? That is 10. That will be the root. What is the second value? 5. 5 will be placed in the left. Now see, is it satisfying the MAX-HEAP? Yes, 10 is greater than 5. Next is 22, that will be inserted at right child. Now when we insert it at right child, we can see from here that it is violating the condition of parent value greater than child value. So we will interchange the two values and we will get 22, 5, 10. Now we got MAX-HEAP. Okay, now what is the next value? That is 2. So we will insert 2 at left position because it is complete binary tree. At last level, we will add the elements from left side. Now see, it is satisfying the property. Yes. So this is the construction of heap tree. Now what we will do in second phase, we will go on deleting the elements and the resultant will be the sorted set. How do we do that? We do that with the help of deletion of root. So I will simply delete root. How will I delete root? I will delete 22. And what will I do for doing the in place sorting? I will exchange it with the last element. Okay, so what will happen here? 2 will come here and 22 here. And I will reduce the heap size. So I deleted it from the main list. But what happened now? I deleted it. I put it at last position. I deleted it. But now what happened? 2 has come here, which is smaller than 5 as well as 10. So I need to maintain again the MAX-HEAP. So I'll compare with the child nodes and will put the maximum value there. So it will be floated. It will flow according to its position when it will get its proper position. So firstly we will build the heap, then we will delete items that will result in sorted list. Now the point is, when we do build heap like this, in this what happened? We took the first element, inserted, second inserted, third inserted and so on. So we do insert each element. How many elements are there in array? N elements. So I need to check the maintenance of max heap for all the n values. That can be reduced with one way. What is that? In this, we are starting with first element and then we are going adding. So I added 4 elements, first, second, third and 4. What else I can do? I take the original array as a complete binary tree as we have discussed on last slide, that this is 10, that is one location, second location, third location, fourth location, 5 will be at left, okay, 22 at right and 2 at left. This is the original position. Okay, so in this we started with 10, then we moved from top to bottom, that is from root to leaves. We went on adding. Now what else we can do? We can go from bottom to top. The second option of building max heap is from bottom to top. In bottom to top, what is the benefit? Why do we prefer this? Because in this we will not do the maintenance for n values. N is the number of items in my array. So I will not do it for n. What I will do it for only non-leaf nodes. Because if I consider this one, this is my leaf node 2. So 2 is already a max heap. One element is always sorted, max heap. 22 is already max heap. So I will start from 5. What is 5? A non-leaf node from bottom. So here I took the top up approach, here I am using bottom up approach. So in this what we will do? We will start from 5 and we'll see, is 5 making the max heap? So 5 is greater than 2, yes, it is already max heap. So what we'll do now? We'll go to one more element backward. Next is our 10. Is 10 forming max heap? No. So we'll simply interchange. So in this case, when we were building heap from top to bottom, we were doing the work for n elements, but in this we are doing only for non-leaf nodes. So that's why we will prefer the method from bottom to top. This is called happify. Okay. So first what will be the first step? That is build max heap. After this slide we'll discuss how it is created. Then for I is equal to length a down to 2. So firstly we will delete first element, that will be out of array, okay, and then we will apply the happify method. Happify will maintain the max heap value. So now let us discuss max happify and build max heap. So firstly build max heap will be called, then for each element of the which is present currently at root, that will be deleted. How it will be deleted? It will be interchanged with the last element. I said, as I told you in this example, the heap size will reduce, but it may create a violation of max heap property. So we will call the max happify method for first element. Why for first element? Because the top root, which was maximum of all, has been deleted and it has been exchanged with the last element. Okay, now the last element has come on the top. So that is our first element. Now root is at first location, first index. So we need to call max happify for that to maintain the max heap. Okay, so that is our algorithm for heap sort. Now let us discuss build max heap and max happify in detail. Okay, so max happify, build max heap and heap sort, these are our procedures. We have discussed the heap sort procedure. Now we'll discuss both the methods max happify and build max heap one by one. First is max happify. What max happify is doing? It is taking an array and one index. Let me say first index. It means it will check the root node is following the property. If it is not, then we will go on swapping it with the other element which is greater. Assume the binary tree rooted at left I. So what we took? We considered ith index element. Let me say this is ith index element, and we considered that left of I means this one. What is that? 2i. Right 2i plus 1. So what we consider, assume the binary tree rooted at left I and right I are already max heap, but ai may be smaller than its children, okay, which is violating the property. As we said on the last slide, that last element we interchanged with the first one to make the in-place sorting algorithm. Okay, so in that case, the first element will be violating the property. So what we are considering, max happify will run when ith index is violating the property, but left I and right I, left subtree of I and right subtree of I are already max heap. Okay, so the max heap let the value of ai floats down in the max heap to maintain the property of max heap. Okay, so we can see this example. Here we have taken this index. The value at index 2 is 4. All others are following the max heap property, but 4 is violating. 4 is less than the child nodes 14 and 7. Okay, so what we will do, we will find out the maximum among these. The maximum among these is 14. So 14 will go above and 4 will be exchanged that. So 4 has been exchanged with this. Now at what new location 4 has gone? It may violate again at that level. So again it will be checked. Now it is, what is maximum among 4 to 8? That is 8. So 8 has been shifted here at above level. So we have maintained the, this is max happify. We have put 4 at its proper location. That is our aim. What is our aim? When ai is violating the property, ai floats down in the max heap. So that is our happify method. This work will be done with happify. So how we will implement it? We will take the left value, we will take the right value, and we will calculate the ith, lth and rth index values, and we will take what is the largest of these. These are the locations: ith location, its left location L, its right location R. Now among these values, which one is largest? So what we will do? If L is less than heap size and AL is greater than AI, then largest will be L, otherwise largest will be I after comparison. Then we are comparing it with R. If AR, the right value, is greater than the largest till now we have found, it may be I or L depending on this condition. So we have already calculated the largest value. So now we will compare that largest value with R. And if R is larger, then we will take R as the largest. Okay. So if the largest is I itself, it means the parent node. I is the parent node, L is the left node, R is the right node. If it is already I, will not do anything. If the parent node is not largest, then we need to exchange it with the largest value. Largest we have just calculated. It will be either I or L or R. So if it is not I, then it will be either L or R. So we will exchange. Now after exchanging, it may be the case that lower level is not fulfilling the max heap property. Okay, so for that we will call max heap for this value, this which we have taken at last. That was largest. It may be left or right as we have calculated here. So this is max heap. It is making the heap again following the property of max heap, means parent value is greater than child node value. So other method is build max heap. Firstly, when we do heap sorting, we create a heap, then we delete element one by one. Okay, so build max heap. So what we have talked about, we are having two approaches. What are the two approaches? Top to down and one is bottom to up. So we have taken the bottom up approach so that we can do less calculations. Okay. So what is build heap? We will take the heap size as length of the array. Okay. And now what is main point to be noted here, that which nodes are leaf nodes and which are non-leaf nodes. Okay. So n by 2, lower bound of n by 2 plus 1 are all leaves. We can see from here, we are having 10 values. If I take 10 by 2, I will get 5. Then plus 1, that is 6. So we can see from here that 6 onwards we are having leaf nodes. We will not do calculation for leaf node. That is the benefit of bottom up approach. That is the benefit of happify method. Okay. So we will start from 5 only. Then we'll do for 4, then for 3, 2, 1. So length a by 2 down to 1. Reverse. Okay. What we are doing? We are applying the happify method from for non-leaf nodes from bottom. Okay, so we are taking length a by 2 down to 1. This is our build max heap. During build max heap also we are calling max happify to maintain the happify max heap property, and same way when we were deleting, we were exchanging that with the last element, then also we were calling happify so that the max heap property can be maintained. So this is one example. We are having values 4, 1, 3, 2, 16, 9, 10, 14, 8, 7. So this is the situation. 4, 1, 3, 2, 16, 9, 10, 14, 8, 7. Now from where we will start? We will start from non-leaf nodes. This is our non-leaf node, first non-leaf node. So we will check it with its child node. It is following the property. Then we'll go one backward. Now one backward is 2. We'll check, is it following the property? No, it is violating. So what we will do? We will compare all the 3 values. The maximum is 14. So 14 will come here and 2 will be shifted to down location. Then we'll go 1 index back. We will do for 3. As 3 is also violating, so we will exchange. Now we will go to next, back, bottom up, and finally we will reach to the root. So all the non-leaf nodes are checked. So what we did, by taking the bottom up approach, we can save the max happify calls for non-leaf nodes. So it is better than if we take top down approach. And at last what we will do, after building this max heap, the first element will be deleted. As we are doing in place deletion, so it will be exchanged with the last element. Okay, so 16 has come at this position and it has been deleted. 16 has been exchanged with 1 and it has come at this location. But when 1 comes here, 1 comes here actually, 1 and 16 are changed and it is deleted. Heap size is decremented, so it has been deleted. Now we will call happify method and we will get in result this. Now what is root now after doing happify? We are having the root 14. Now 14 will be exchanged with the last element. Now what is the last element? 1. Again happify will be called. Then we will delete the next root, then the next root, and so on. So one by one we are going on deleting the root and finally we are able to get the sorted array. So what we did, we have the first call to build max heap. In build max heap, what we did, we use the happify method so that building heap property can be saved for leaf nodes. We will do only for non-leaf nodes. Okay, then after building the max heap, what we did, we exchange the root node with the last element and then we decrease the heap size. So finally what we are getting, that is the sorted array. This is heap sort method. So in this particular lecture, we talked about heap sorting and we discussed top down and bottom up both the approach, and finally we implemented the heap sort with happify method. Thank you. Jai Hind.